So we'll continue our discussion on the second method, MMM method or Rother's ampere turns method. It's okay. MMM method, magnetic motive force method. MMF stands for magnetic motive force here. Okay. So what is the drawback of EMM method? EMM method drawback is we are getting percentage voltage regulation. We are getting the more than the actual value. Because we are getting the percentage voltage regulation more than the actual. Why? Because I am considering it as entire XL as okay, even XA as XL. Okay, complete armature reactance is considered as leakage reactance. Now here in the MMM method, okay, what I will try to do here, okay, I will try to consider okay XL as XA. It is in the reverse manner. I will try to consider entire leakage reactance as armature reactance. Why I am stressing this is so many times asked. Okay, these bits are entire leakage reactance is considered in terms of armature reactance. Actually, there are two parameters are there. In EMM method, entire armature reactance is considered as leakage reactance. Only that means I am assuming that there is only one person is there. There is leakage reactance. In the MMM method, out of XL and XA and XL, I am only considering as XA. I am assuming that all the XL is equal to the XA, but the characteristics might not be same. So as I am considering that XL entire armature leakage reactance as XA here, then XS is equal to XS is approximately assumed as XA here. Okay, so XS is assumed as XA here. Because of this, okay, I am directly concluding in the starting itself. Whatever the percentage voltage regulation that I am getting here, this is less than the actual. This is less than the actual. In the previous case, what we got here, as entire leakage reactance is armature reactance is considered as leakage reactance, I am getting the more than the actual value, percentage regulation. Okay. Whereas in the second case here, now in this case here, what I am getting here, as leakage reactance is also considered in terms of armature reactance. Okay, I am getting the percentage voltage regulation measured value is less than the actual. If 35 is the actual percentage voltage regulation, EMF we are getting 45, MMF I am getting 25. Is both values are desirable? Acceptable up to some extent, but we are not able to get the exact value. Okay, so this is what the difference between the MMF method and EMM method. In conclusion, we will try to discuss how we are going to do here. The scientist who found this Rother's MMF method. Again, we will try to which characteristics we will try to use here. We will try to use OCC characteristics as well as short circuit characteristics here. Okay. So again, there are two let me try to use we will try to draw this MMM method by using here. Okay, is it clear? Okay, so here in the MMM method, again we will try to use OCC as well as short circuit characteristics. OCC is drawn between E0 versus IF. Short circuit is drawn between ISC versus IF. Okay, so what I will try to do here, first same draw OCC characteristics. Next, here this is E0 versus IF. This is ISC. Okay, versus IF. Sometimes you can also represent this in the other side rather than this. Okay, I am trying to represent here. So I can also in some books it will also be represented here, that is ISC. Both are correct. That means the reference point itself is from this point only. Okay, now whether it represent left side or right side, okay, the characteristics will be remain same. This is IF and this is E0. Okay, this is OCC. And what about this? This is short circuit characteristics. Okay, now here from this we will try to measure two important parameters, that is IFM. What is IFM here? Main field current required to generate rated voltage. What is IFM? IFM stands for is under no load voltage. Under no loads. What is IFM? Main field current required to generate rated voltage under no load condition. Main field current required to generate rated voltage under no load condition. Okay, so here let's see that if I want to represent, let's assume that this is the rated voltage. Okay, to generate this rated voltage I require some current here. That current that field current I'm considering it as IFM. IFM is nothing but main field current required to generate rated no load voltage. Is that clear or not? So we will also discuss one more term, that is IFA. Notations will be different in, maybe different in some other textbooks here. IFA. What is this IFA? Main field current required to generate rated current. Main field current required to generate rated current under short circuit condition. These two things are important here. Okay, rated voltage here, rated current here. Okay, IFA stands for main field current required to generate rated current under short circuit condition. Main field current required to generate rated current under short circuit condition. Okay, under short circuit condition. So how can I, so let's assume that, so we have wantedly have kept this in the right side so that you will be habituated here. So now here let's assume that this point is rated currents. Okay, rated current is nothing but maximum load applied. Okay, okay, 100% load here. For this, what is this point here? This point is corresponding intersection point, and this point I am going to say that IFA here. Okay, this A point is this OA, and this point is B here. This IFA is, IFM length is OA, IFA length is OB length. This is the rated current required to generate the main field current required to generate rated current under short circuit condition. This is IFM and this is IFA. This method is comparatively easy. Okay, so after finding these two here, what I am supposed to do here? Okay, is that clear so far? Okay, so what I will do here, there will be again, what are the three power factor cases here? We have unity power factor load, lagging power factor, as well as leading power factor. Lagging power factor is nothing but it's a combination of R and L. We will not get any pure inductor. Leading condition is combination of R and C. We will not get any pure capacitor. Okay, even your mobile battery is also pure capacitor. Okay, if you keep it aside, okay, the battery will drain. It's because of the resistance present in the battery. Okay, now, okay, so here the phasor relation, let's assume that for a phasor relations here, for a unity power factor, if this is a IFM here, IFM phasor, okay, then this will be IFA. Okay, this phasor is IFA. Now, if this value is some 3 and if this value is 2, can I directly add 3 plus 2 as 5? Resultant value. The resultant value I am considering it as IFT. I need to find out total field current here. Remember, okay, I am repeating again here. Just now we calculated two parameters here, IFM and as well as IFA. IFM stands for main field current, IFA stands for the two currents we calculated. Both are not arithmetic values. These are all two are phasor parameters. These are actually, if I want to represent in the diagram, one is for a unity power factor. So both are shifting by how much angle? 90 degrees. So now what is the resultant IFT here? It's a phasor sum of these two here. So I can directly write here IFT is the phasor sum of IFM plus IFE. Okay, IFM phasor plus IFA phasor. Okay, now for a lagging power factor, okay, now here if this is IFM, okay, if this is IFM, actually IFA for a unity power factor, here it should be there here. What actually happening here? IFA is shifting, okay, IFA is shifting here. This is the dotted line here. So it should be for a unity power factor, it should be in the white line here. But it is shifting by how much angle here? It's shifting by phi angle, where phi is What is phi? Phase angle. Phi is the phase angle. It is shifting right towards the phase angle here. So now what is the resultant phasor sum here? The phasor sum is, this is the IFT here. And what is the total angle here? Total angle is 90 plus phi. Okay, I will use this all this for concluding the formulas. Okay, this is 90 plus phi. Okay, similarly for a leading power factor, okay, for a leading power factor, if I assume this as IFM, okay, and dotted line, it should be there in the unity power factor, but actually what's actually happening here, the current is, IFM current is coming ahead, okay, current is coming ahead here. So what is this here? Again it is phi. This phi is leading, this phi is lagging, okay, and the resultant of these two will be, what is the resultant of these two here? These two will be IFT. Now what is the net angle here? Previously the total angle is 90 plus phi here. It is phi has to be considered added or subtracted. It has to be subtracted. Now it is 90 minus phi here. It has to be 90 minus phi here. So for three different cases we can able to see here. One is unity power factor, it is 90 degrees. For unity power factor the angle is 90 degrees. For a lagging power factor it is 90 plus phi. For a leading power factor it is 90 minus phi here. Okay. So if you have only one single value, directly I can write it as IFT equal to under root of IFM square plus IFA square. But we have lagging power factor as well as leading power factor. Can I say that don't use inductive loads, don't use capacitive loads, you use only resistive load, as with the formula is simple? You cannot say that. Okay. Whatever the load, we should be in a position to find out the voltage regulation here. So the combining, I will try to write down the generalized formula here. The generalized formula for this is, the simplified formula is IFT equal to IFM square plus IFA square plus 2 into IFM into IFA into cos of 180 minus 90 plus phi. The preferred formula. Okay, it avoids no negative values. Okay, you can simplify the other formulas and you can write minus also. Okay, but just it's slightly complicated. Okay, so in other textbook the formula will be different here. Just kindly note on this formula. So IFT equal to under root of IFM square plus IFA square plus 2 into IFM into IFA into cos of 180 minus 90 plus phi. Cos 180 minus all silver teacups. So 180 cos of 180 minus theta minus cos theta. So you can also rewrite here minus of 2fm into IFA into cos of 90 plus phi also you can write. Okay, in some other textbooks, whatever you want to write, but confined to fix to one value, one formula. Okay, in some other textbook the formula just simplified here, as everyone is maths based students here, you can simplify it, but stick to one formula here. So what is the conclusion here? We got this IFM from the graph. We got IFM from the graph and IFA from the graph. Can I able to calculate IFT or not? This IFT and 180 here. What is the important thing here? 90 plus or minus phi here. Where plus is for lagging and minus is for leading here. Okay. Wantedly I have kept here 90 plus phi. Okay. It is 90 minus phi. To make sure that why I have to write 90 plus phi for lagging? Why I have to write 90 minus phi for leading? Okay. So this is the formula for finding IFT. I hope it's clear. Once IFT is came, just we have to draw add one single step that concludes the formula graph here. After getting, let's assume that I got this. Let's assume that I got this point as, at this point I got IFT, total field current here. Phasor sum of IFM plus IFE. Okay, what I have to do here? I have to extrapolate. I have to write down this word. I have to extrapolate it to, okay, onto which point? OCC. I'm not able to dictate the points here. Only thing is, what are the points that I'm explaining, you should be in a position to write down in the exam if you get for a theory question. Extrapolate IFT onto the OCC. That means drawing a dotted lines. And from OCC extrapolate onto the y-axis. So this value, whatever you're getting here, this is E naught. This is E naught. Okay. Finally, what I want here to get percentage voltage regulation. To get percentage voltage regulation, I need E naught minus V by V here. Already we know V naught V. Now I am finding E naught. Once E naught is calculated, can I able to calculate percentage voltage regulation? Yes, I can able to calculate percentage voltage regulation. This is how I can able to calculate percentage voltage regulation by this is which method? MMF method or ampere turns method. Why it is ampere turns? The units of MMF. MMF is units is ampere turns. That's why it is also called as ampere turn method. This is how we need to calculate the phase MMF voltage regulation by using MMF method. So we calculated OCC character drop. Next is short circuit characteristics. Next we calculated we measured IFM and IFA. The phasor sum of IFM and IFA for different phase loads we have drawn, and correspondingly we have concluded a single formula. You can further reduce and we can modify as per your requirement. Once IFT is drawn, we have to locate the point on the graph and extrapolate into the OCC curve. From that, extrapolate into the y-axis and find out the point on E naught. Find out the point E naught. Substitute the point E naught in the voltage regulation formula. E naught minus V by V will get percentage voltage regulation. So what we concluded here, again we are not connecting any load here, just we are taking two characteristics, OCC as well as AC. And what is the drawback here? Are we getting the exact value of percentage voltage regulation? We are getting the less than the percentage voltage regulation measured is less than the percentage regulation actual. Okay, this is how the voltage regulation of MMF method can be calculated, okay, by using MMF method.